Hi everyone, it's Adam again. So today I'm just going to finish the chapter on complex numbers. So this will be the second video, complex numbers, and the last one. Okay. So there's one thing that I just forgot to mention in the last video, which I probably should have. Basically, if you have some polynomials, so a polynomial is just when you have something like this. So you just have something like this. So in this case, this would be just a constant. This would be a linear part. This is a quadratic part. Then you have cubic, quartic, quintic, up, and you keep going up and up and up. The degree of a polynomial is this. Okay, that's all you need to know. You need to know the degree of f of x, in this case, is n. And the number of roots is n. That is absolutely all you need to know. Okay, all you need to know is that if you have a quadratic, it always says that's x squared. So that would be, you'd have 2 roots. If it's cubic, you have 3 roots. If the highest power is a power to the 4, then there's 4 roots, and so on and so on. That is all you need to know from this. Okay? Another thing that I would like to look at is just a couple of rules. So the complex conjugate that I covered in the last video. So let's say Z1 is A plus BI. The complex conjugate, which is Z1 bar, is equal to A minus BI. So you just change this plus to a minus. And that's it. Okay? So they can ask you, so just the modulus of z is also equal to the square root of z bar. So it's just another way of saying it. And remember, z bar is a squared plus b squared. Okay? So that's basically where you'd use the complex conjugate. Okay? Where if z is equal to a plus bi. Like this. Okay, so actually I might just get rid of this one. Okay. So that's kind of all with that. And now we're getting on to the very, very important part of this chapter, which is kind of polar form and then going into the Moivre's theorem. So what is polar form? So polar form basically is circle. Okay? For those of you who have seen the unit circle, this is basically just the unit circle, okay? But for those of you who haven't seen the unit circle, basically, you don't need to really know any of that, okay? Doesn't really matter. So all we're saying is, let's say we have an imaginary axis and a real axis. So again, this is your Argand diagram. And we have some z, which is here, which is some a plus bi. Instead of writing z as a plus bi, we want to write it in polar form, which is basically you want to write it in circle form. So you might say circle form, what does that mean? That's basically, you want to write it as a radius and an angle theta rather than an x value and a y value. You want to write it as how long is it and what angle does it have. Okay? So z, you can write it as a plus bi, but you could also write it as r cos theta plus I sine theta. Okay, now this might be very awkward right now, but a is just equal to r cos theta, and b is simply equal to r sine theta. Okay? So this part here is just r cos theta, and this is r sine theta. And just to confirm, you can say, okay, well, cos theta is equal to what? Cos of theta in this triangle is the adjacent over the hypotenuse, which is b over r. Therefore, r, wait, sorry, did I do this wrong? Yeah, I put these the wrong way around. Sorry. Sorry about that. Sorry, this should be A and this should be B. So remember, A is the real part, so it goes along the real line, and then B is the imaginary part, so it goes up. Okay, sorry about that. So in this case, cos is the adjacent, which in this case is A. So I can say that R cos theta, that's equal to R times A over R, which is just A. Okay? So A is just equal to R cos theta. And for similar reasons, B is equal to R sin theta. So you can also write it as this way. And this is why it's called polar form, because instead of writing it in an X value and a Y value, you have a radius and then you have an angle. And it tells you where the point Z is. Okay? Let's do an example. Let's say they ask you that, or they tell you Z is going to be minus root 3 plus I. And they ask you to write this in polar form. So typically, this is called rectangular form, and this is called polar form. So if they ask you to do this in polar form, the easiest thing to do is to look and just draw it roughly. So I is just 1. So I might just draw it up here just to be a bit, and then root 3 is over here. So it's a little bit, root 3 is bigger than 1. So it's probably somewhere over here. Now, very, very important. Theta is always measured from this axis here, and it is always measured anti-clockwise. Very, very, very important. Okay? So please do not get that mixed up. Theta is always this angle, it always goes backwards like this. Okay? So in this case, you would go from there to there. So you go backwards like that. Here, I'm going back a bit further, but you always go anti-clockwise. Okay? From this axis here. Okay, so this is 1, and this is root 3. So remember, it's minus root 3 plus 1i. So the 1 goes up, and then the root 3 goes left, and that's why it's this way. So now, I want to know what angle is this? Because, okay, and another thing is we're also going to use radians. Okay, so radians, basically 180 degrees is equal to pi radians. Okay, that's the only conversion you need to know. All right. So, first of all, I want to know what is the radius. So what is r? So how long is this? Well, again, I can use Pythagoras. I can say r squared is equal to 1 squared plus root 3 squared. That's 1 plus 3, that's 4. So r is the square root of 4. So r is 2. So the radius is 2. Perfect. The next thing I need to do is I need to figure out the angle. So the angle, I can say, well, the tan of alpha is the opposite over the adjacent, which in this case is 1 over root 3. Okay? Now, if you wanted to, you could also say that the tan of theta is equal to, it's going to be the imaginary over the real. So this would always work. Okay, and it will give you the right answer straight away if you wanted a formula for it. But I just think this way is a bit more kind of intuitive or easy to understand. But this formula would work for theta if you just put the imaginary over the real and then said that theta was equal to 10 minus 1 of that. You'd get theta properly, okay? So, that's that. And then here we have tan alpha is equal to 1 over root 3. So alpha is equal to tan minus 1 of 1 over root 3. And this is equal to pi over 6. Or, sorry, this is equal to 30 degrees. Now, again, if you had your calculator in radians, you get that this is pi over 6. But to go from degrees to radians, you basically multiply by pi and divide by 180. Because remember, pi is equal to 180, and therefore if I multiply by pi over 180, I'm multiplying it by 1. Okay? Just to be clear about that. All right? So this is equal to pi over 6. And that's what you would have gotten here. So if alpha is pi over 6, then I can say theta is just 180 degrees minus alpha. So theta is 180 minus alpha. 180 is pi. Alpha is pi over 6. So it's 5 pi over 6. Okay? So z, which is minus root 3, plus I, this is also equal to 2 times cos of theta, which is 5 pi over 6, plus I sine 5 pi over 6. So this and this are the same thing. And if you don't believe me, plug it into your calculator. You'll see that the cos of 5 pi over 6 is going to be minus root 3 over 2. And the sine of 5 pi over 6 is just going to be equal to a half. So if you plug these up in here, you will just end up back at this. Okay? Theta can also be called the argument. Or the ARG of Z. Okay, and R is just the modulus. Or length, which is what we covered in the last video. But theta is just called the argument. So you always measure it from the right hand side of the axis. Okay? Alright. So now, another thing that I'm going to do is there's a question here in the book, which is much, much easier if you just think about it. Okay, so Z1, you're told is 3 times the cos of pi over 6 plus I sine pi over 6. And Z2 is equal to 4 cos pi over 3 plus I sine pi over 3. Okay, so these are two complex numbers. All right. Now, they ask you what is Z1 multiplied by Z2. So, the best way to think about this is when you multiply complex numbers. Okay, just listen very carefully to what I'm saying. When you multiply complex numbers, you add their angles and you multiply their lengths. Okay, this will save you a world of trouble. Okay, that's all it is. You just, when you multiply complex numbers, you add their angles or you add their arguments and you multiply their lengths. So Z1 times Z2 is equal to 3 times 4, that's 12. It's the cos, so again you add the angles, so pi over 6 plus pi over 3, that's pi over 6 plus 2 pi over 6, which is 3 pi over 6. Which is equal to 12 cos pi over 2 plus I sine pi over 2. Like that. If you plug it into your calculator, the cos of pi over 2 will be equal to 0. And the sine is just equal to 1. So this is just equal to 12i. Okay? So that's how you do those. Okay, so that saves you a world of pain, because if you didn't do it, you would have to plug these into your calculator, multiply them out normally, and it would be a little bit painful. Okay? The same way, if I asked you, what's Z2 divided by Z1? Again, now you're dividing, so you divide their lengths and you minus their angles, okay? So the length, 4 divided by 3 is just 4 over 3, times the cos, minus the angles, pi over 3 minus pi over 6, that's just pi over 6. Pi over 6 like that. And boom, done. So just in one quick sweep like that, you're completely finished. Okay? So just to be careful with that. Okay? And it's a very handy thing to know that if you're multiplying complex numbers, you add their angles, multiply their lengths. If you're dividing complex numbers, you divide their lengths and minus their angles. Okay? Now, that'll give you some intuition as to why de Moivre's theorem is the way it is. So what is de Moivre's theorem? De Moivre's theorem basically says that if you have z is equal to r cos theta plus I sin theta, then z to the power of n is r to the power of n cos n theta plus I sin n theta. Like this. So basically, if you multiply z by itself n times, then you just multiply its length by itself n times, and you add its angle to itself n times. That's it. That's all de Moivre's theorem is saying. Okay, very, very important theorem, but quite easy once you realize that, oh, well, if I multiply two complex numbers, I multiply their lengths and I add their angles. So if I multiply a length by itself n times, I just get r to the power of n. And if I add an angle to itself n times, then I just get n times theta. Because there's n of them. You're adding n of them, and then therefore you have n of them. Okay? Now, I will prove this by induction. I'm going to prove this for all n is an element of n. But this is true for n is an element of z. You can be asked to prove it. I don't think the proof for all whole numbers has ever come up. I think this may have come up. So it is one thing that it might be handy to just go through once, okay? So again, it's true for n is an element of n, so n is 1, 2, 3, ... So remember, proof by induction is you prove it for the smallest number. So I show that it's true for n equals 1. So is z to the power of 1 equal to r to the power of 1 cos of 1 times theta, which is theta, plus I sin theta? Yeah, it is. It obviously is. Step 2, you assume it's true for n equals k. So you assume that z to the power of k is equal to r to the power of k cos k theta plus I sin k theta. And now the third step, because that is true, I need to show that if n equals k plus 1, we get that z to the k plus 1 is equal to r to the k plus 1 into cos k theta, k theta plus theta. So that's just k plus 1 plus I sin k theta plus theta. Like so. Okay? So, I'm just going to massage the left-hand side. Okay? So what I need to do is, I need to show that this thing is this thing. Okay, so what does that mean? That means I need to show that r cos theta plus I sin theta to the power of k plus 1 is equal to r to the k plus 1 times cos k theta plus I sin k theta plus theta. Now, hopefully it's obvious that I can just get rid of the r's, because obviously it's just going to be r to the k plus 1 on the left and the right. So what I really need to show, I need to show that cos theta plus I sin theta to the power of k plus 1. Again, for n equals k, this is the same thing as get rid of this, that cos theta plus I sin theta to the power of k is equal to this. So this is what we have. And this is what I need to show, that this is cos k theta plus I sin k theta plus theta. Okay? So on the left hand side, this is cos theta plus I sine theta to the power of k multiplied by cos theta plus I sine theta. Well, I know that this is equal to this, which is equal to this by assumption. So I can replace this with cos k theta plus I sine k theta times cos theta plus I sine theta. Okay? So hopefully that's all okay so far. So now I'm going to multiply this together. So I get that it's cos k theta cos theta plus I sine theta cos k theta plus I sine k theta cos theta. Then it's this one times this one. So it's I times I, which is minus 1. So it's minus sine k theta sine theta. This now is equal to cos k theta minus sine k theta sine theta plus I times sine theta cos k theta plus sine k theta cos theta. Okay. And now, using your log tables, you will find that this is the formula for cos A plus B, and this is the formula for sine A plus B. So that is what you get. So by induction, these two things are the same thing. Okay? So this is fine. Okay. So now that we've done that, I'll do 2 or 3 examples and then I think I'll leave it there for today. Okay? So one thing it might say, use the Moivre's theorem to expand 1 plus I to the power of 10 in A plus BI. Okay? Very first thing, you put this in polar form. You draw it out. This is always just a quick sketch where that's 1 and that's 1. This is R, this is theta. You can probably guess that theta is 45 degrees, which is pi over 4. Okay? So again, 45 degrees is a quarter of 180, and therefore it's a quarter of pi. Remember that pi is 180 degrees. The length, r squared, is equal to 1 squared plus 1 squared, which is 2. So r equals the square root of 2, like so. So 1 plus I is equal to root 2 cos of pi over 4 plus I sine pi over 4. So 1 plus I to the power of 10 is equal to root 2 to the power of 10 cos. So now you multiply the pi over 4 by 10. Okay, so it's 10 pi over 4, which is 5 pi over 2. Like so. Root 2 to the power of 10, that's 2 to the power of 5, which should be 32, 64, 32. Yeah, definitely 32. The cos of 5 pi over 2 should be 0. And the sine of 5 pi over 2 should be 1. So it's just 1i. So the answer is just 32i. So if they ask you to do something like this, this is basically what they're hinting at. Okay, now that's important because they mightn't tell you that it's going to be, they mightn't tell you that it's going to be the Moivre's theorem. You're going to be expected to know it. Okay, so that's the Moivre's theorem. Okay, and very last one. They might say, solve z to the power of 4 is equal to minus 2 minus 2 root 3. So how would you solve this? Okay. Very first thing you would do, you would write this in polar form. So again, you draw it out. You say, okay, so it's minus 2 root 3, so it looks something like this. Where this is 2 root 3, this is 2. Angle here, okay, so sorry, I won't use theta, I'll use alpha. Because remember, theta is this angle here, from this axis all the way down here. This is theta. So alpha, I can say the tan of alpha is the opposite, which is 2 root 3 over 2, which is root 3. So alpha is just going to be 60, which is pi over 3. So theta is going to be pi plus pi over 3. So theta is just 4 pi over 3. Okay? The next thing I want to do is I want to figure out the length. So I can say r squared, again using Pythagoras, r squared is equal to 2 squared, which is 4. 2 root 3 squared, that's 4 times 3, which is 12. Okay, so 16. So r is root 16, which is 4. So z to the power of 4 is equal to omega, which is equal to 4 cos 4 pi over 3 plus I sine 4 pi over 3. Okay? Now, the next thing that is very, very important is that I can say, well, z is going to be 4 cos 4 pi over 3 plus I sine 4 pi over 3, all to the power of 1 over 4. So this equals, so to the power of 1 over 4, so 4 to the power of 1 over 4 is root 2. Now you multiply it into the angles. So remember back up in the Moivre's theorem, you'd multiply you multiply by the angle and then you do the length to the power. So it's 4 to the power of a quarter is root 2. A quarter times 4 pi over 3 is just pi over 3. So that's z. That's z1. That's the first answer. Now, I said before, and hopefully you'll remember, how many solutions should this have? The answer is 4. It should have 4 different solutions. Okay? The way you find them is, you draw this out, because we have one solution, which is going to be root 2, pi over 3, that's 60 degrees, so it's somewhere up here. To find the other 4, what you do is you split the page into 4 equal parts. Make all the lines the same length, like so. This would be Z2, Z3, Z4, where all of these are going to be at 90 degrees. So you're just adding 90 every single time. So Z1 is this. So Z1 is just pi over 3. Z2 is just going to be root 2 cos pi over 3 plus pi over 2. So you just add 90. Z3 and Z4 are the exact same. But instead, you add pi or 3 pi over 2. So you add, sorry, I might just finish this. So to get from Z1 to Z2, you add pi over 4. Sorry, pi over 2. Then you add pi over 2. And then you add pi over 2 again. And the way you decide what this number should be, it's simply 2 pi divided by n, where n is the z to the n equals whatever. So in this case, we have z to the 4. Back up here, and therefore you add on 2 pi divided by 4. 2 pi over 4 is just simply pi over 2. And that's where these come from. And you keep doing it. Okay? And you might ask, well, why do we stop here? Why can't I add pi over 2 again? If you add pi over 2 again, you'd be adding 2 pi. And that's 360. So if you add 2 pi again, so you add 2 pi once, then you do it again and again. If you did it another time, you'd get back to Z1 again. So you wouldn't have a new answer. Okay? And just to be clear, if there was 3 answers, and let's say one answer was here, then the second answer would be up here, and the third answer would be down here, where these would be 120. Okay, so you basically just pick 360 and divide it by how many answers you have. So if this was Z cubed is equal to something, this is what you do. Okay? So yeah, I think that could be it for complex numbers. I think I've covered everything. Don't think there's anything I've forgotten. So yeah, I think I'm happy to leave it there for this video. So in the next videos, I'll be going over calculus, which is by far my favorite subject. I think it's really, really interesting. And I do think that once the majority of students will get a hold of it, I do think it'll be their favorite one too. It's the most interesting one. So yeah, I think I will leave it there for today. So thanks very much for tuning in, and I'll talk to you in the next one. Bye.